So Peter's a professor in mathematics at UNO, international expert on theoretical aspects of loophole-free Bell tests. And today he's going to tell us about his ongoing research projects. Thanks.
Thanks, Mark. Okay, so now thank you for that introduction. Now I'm going to enter the pressing of the share screen and hope that that works okay. Okay. Okay, how does that look for everyone?
Looks good.
Okay, great. All right, yeah, so my talk today is Tsirelson polytopes and device-independent quantum information. Yeah, so we're going to talk about polytope approximations to the quantum set and applications to device-independent random number generation. So we're going to talk mostly about that first bullet point. When we get to that second bullet point, I'm going to have to do a little bit more of like a high-level overview because it gets a little technical, but hopefully I can at least give you the flavor of it. And then I'll finish up with some talk about current research directions and work that I'm doing right now at UNO and positions that we're going to be having open. So, so let's start with polytope approximations to the quantum set. So a lot of you are probably asking, what is the quantum set? What are polytopes? So we'll start with the quantum set. And I want to consider a behavior. Okay, so this is a set of conditional probabilities that correspond to an experiment. So let's think about this table a little bit. What have I written here? In some of my talks, I like to draw a little a picture of two measuring stations separated by a big distance, one with Alice and one with Bob. For the Zoom talk, I'm not doing that, but we have, two measuring stations, and they're measuring an entangled particle. That's kind of the paradigm we're thinking about. And so, or an entangled pair of particles. And so Alice is maybe over here, and Bob is over here. Or I can indicate that with my mouse. We've got like Alice is over here, Bob is over there. In the middle, we've got something that's sending particles to Alice and particles to Bob. They're entangled with each other. And Alice and Bob have these two different measurement settings. And so there's a range of probabilities corresponding to particular settings and outcomes that can happen in this experiment. So let's look at this row here. Alice has two different, so I've highlighted this probability in red. Alice has two different measurement settings she can choose. One of these settings is denoted with A, the other setting is denoted with A prime. And Bob has two different settings he can choose, B or B prime. And so generally what this might be is they might be polarization settings if they're measuring photons. Alice could pass her photon through a polarization filter before it hits a detector. And so there might be two different ways she could rotate that polarization filter. That would correspond to A and A prime being the two different ways she could rotate her polarization filter. But in just a more abstract sense, we just say that Alice has some measuring device. That measuring device can have two settings on it. We call those two settings A and A prime. And then Alice can either see a click or she cannot see a click. She can either, it's a dichotomous measurement. She either sees something or she doesn't. So we're going to call seeing something, we're going to call that plus, and not seeing something, we're going to call that 0. And so hopefully now you're getting some sense for this table that 0.0732, as I've said down here, is the probability that Alice sees a click and Bob sees as no click, given that Alice has her apparatus on setting A prime and Bob has his setting on setting B. So this is Alice having her setting A prime, Bob having his setting B, Alice seeing a click, Bob not seeing a click. So, the Alice comes first, so the plus followed by the 0 means Alice sees something Bob doesn't. Now, all of these probabilities altogether are a behavior. This is a defined term, which is just a set of conditional probabilities that correspond to an experiment. So Bob and Alice, they run this experiment under the 4 different measurement configurations. They record their data. They do this, millions of times. They get some probabilities, and these are maybe the probabilities they see. The probabilities I've actually filled out in this table are the probabilities that would maximally violate the CHSH inequality. Those can be obtained by measuring a maximally entangled state, a singlet state, in specific configuration. So these probabilities don't need to look like this. They could look like something else, but this is just one example of some probabilities that can be obtained by performing a quantum measurement on a quantum system. And so a behavior refers to all 16 of these conditional probabilities. It can be represented as an element of R16, the 16-dimensional vector space. And only some behaviors can be achieved by quantum states and measurements. So the quantum set is the set of all vectors in R16 that correspond to probability distributions that you can obtain by performing a quantum measurement on a quantum system. Okay, so that's kind of the main thing here. The quantum set is every vector of probabilities that can come from a valid quantum measurement. And there are some, you could fill this table with some probabilities that cannot be obtained by measuring a quantum system. So what we're going to be talking a lot about is, sort of thinking about these set of quantum achievable probabilities and saying, how can we sort of describe that set as a subset of R16, a 16-dimensional vector space, that'll allow us to sort of get a sense for, what probability distributions are quantum and which ones are not. So going back to my first slide, I'm talking about polytope approximations to the quantum set. So hopefully I've described the quantum set pretty well. And now I'm going to answer the second question you probably had, which is, what is a polytope? What is a polytope approximation? So the quantum set is these vectors in R16 corresponding to valid quantum measurements and the probabilities that they would engender. And what is a polytope? Well, here's an example of a polytope. Think polygon in a higher dimensional space. I think that's just the best thing for this talk is just, think of R16 and think of some sort of polygon, a bounded polygon in that space. Now, let's talk about R3, the 3-dimensional vector space, which is something we can actually visualize. And here I've drawn a polytope of valid probability distributions in R3. Okay, here are some, and I've got 3 valid probability distributions at the bottom here. If you have a probability distribution over 3 outcomes, then you're going to have a vector in R3. And the first 2 things I've written here are valid probability distributions in R3. And the third thing is a vector in R3 that is not a valid probability distribution. So in this picture, this little simplex, this triangle, is I've plotted the coordinates of all valid probability distributions over 3 outcomes, right? So let's look at this middle one here, x, y, z equals 0, 1, 0. That would be, where in this picture is that? That's right here. That's y coordinate of 1, x coordinate of 0, z coordinate of 0. So this point corresponds to this probability distribution, and this would be the probability distribution where there's 3 things that can happen, but one of them always happens with probability 1. But then we also have other points in this polytope. We've got, 0.2, 0.3, 0.5. This would be x happens with probability 20%, y happens with probability 30%, and z happens with probability 50%. And we can think, okay, that's somewhere in the middle of this triangle. The x coordinate is 0.2, that's about here. The y coordinate is about 0.3, that's about here. And the z coordinate is about 0.5, that's about halfway up. You know, so imagine, where do those coordinates come out? Well, that, you know, think about this triangle which joins these points. That would be about here on this triangle. Okay, so this point is a valid probability distribution. It's about here on this triangle. But then this last point, you know, x comma y comma z, 0 comma 3 comma 4. This is a y coordinate of 3 and a z coordinate of 4. That would be way up here in the upper right-hand corner. That's nowhere near this triangle. It's not in there. So a polytope is just a polygon in a higher dimensional space. And a lot of the time when we're dealing with spaces of probability distributions, we end up finding polytopes. Not all the time. Sometimes we have sort of curved boundaries and it's not polygonal, but we're going to be talking about a lot of these polygons of probability distributions. Now, the last thing I want to say about this is that I've just given all the valid probability distributions. Anything that's a valid probability distribution over 3 outcomes is somewhere on this triangle. But, you know, not always is every valid probability distribution going to be quantum. Like, for instance, if we had some 3-level system, you know, and we performed a measurement, a 3-level measurement on it, a projective measurement. Let's suppose that 3-level system were in a mixed state and you perform a projective measurement on it, then you're not going to be able to get some sort of a probability distribution that looks like this middle probability distribution where you get y with probability 1. You could vary your projection directions and you might get different valid probability distributions, but maybe the quantum set of valid probability distributions could just be some stuff sort of in the middle of this triangle, and then there would be some distributions, probability distributions, that you would not be able to obtain by measuring this particular mixed state. So we're going to be talking about subsets of probability distributions that are valid quantum distributions. So now we're going to talk about, go back to our R16 mindset. So I showed you something in R3, but you remember the behavior I showed you at the beginning of the slide had 16 different entries. So now we're dealing with a 16-dimensional space of probability distributions. And we can only look at lower dimensional slices of this 16-dimensional space of behaviors. And it looks something like this. One particular slice of this 16-dimensional set is going to have, you know, sort of a circular shape corresponding to quantum behaviors. And then the quantum behaviors contains strictly these local deterministic behaviors. These are sort of classical distributions that would not display any funny properties of entanglement. But then the quantum set is strictly contained within a larger set of no signaling distributions. And there's an even larger set of just valid probability distributions that would contain even this no signaling set. And so I'll discuss what these no signaling probability distributions are in a second. But the main takeaway here is that in our 16-dimensional space of valid probability distributions in the CHSH-Bell scenario, the quantum set is not like a polygon. It's like a circle, or it has a curved boundary, but it turns out we can contain it in these larger polygons. So I mean, let's ignore these dashed lines for now. And let me just talk about how I can contain the quantum set of valid probability distributions within this larger no signaling set. So going on to our next slide, we have constraints delimiting the polytopes that contain the space of quantum valid probability distributions. So first, we can say that any probability distribution has to satisfy the condition that all probabilities are non-negative and sum to 1. Okay, so we have that, you know, when Alice and Bob choose settings A and B, the set of all possible outcomes, which is plus, plus, plus 0, 0, plus, and 0, 0, that all has to add up to 1. And this holds for all the different measurement configurations. And there's 4 different measurement configurations. So, going back to I'm going to go back a couple slides. Going back to this behavior, what we're just saying is that if something's going to be a valid vector in R16 corresponding to a quantum distribution of probabilities, it better at least be a valid probability distribution. And then each row needs to sum up to 1 because each row corresponds to all the possibilities for one particular setting configuration. So we have 4 little constraints like that. And now going back to our current slide, so we have these probability constraints. And then we have some interesting ones here is that all quantum behaviors must obey the no signaling conditions. This says that if Alice, is at one location and Bob is at another location, and they're simultaneously measuring some entangled particle, that means that if Alice chooses configuration A or versus configuration A prime, that Bob's measurement statistics should not change. So these conditions express that idea that, we're talking about separated Alice and separated Bob, and that Alice's measurement setting should not affect Bob's outcome, his click probability. And because we imagine them separated at great distance, so, if this were true, Alice could send signals to Bob by changing her measurement setting. So, and quantum mechanics respects this. This is a consequence of special relativity. So these are some linear constraints. And when we're working in our big 16-dimensional space, these create sort of like hyperplanes, cutting through the space of valid probability distributions. And they're reduced the dimension of the valid distributions. And so we think that all of these linear constraints, we start with this big probability simplex that looks kind of like that triangle that I had a few slides ago. And then we start chopping it into pieces with these constraints down here, these no signaling constraints. And so we've reduced the set of valid probabilities. And we still have something kind of polygonal, because when you start with a polygon and you intersect it with some hyperplanes, you're still going to get a polygon. That's hopefully a little bit intuitive. Okay, so we've got a polygon containing the quantum set of probabilities. Why do we care? And we care because if we've got a polygon like this no signaling polygon, or polytope, that's the proper word, and it contains the quantum set, and we do have this no signaling polytope that's characterized by those no signaling conditions on the previous slide, then if we can say something holds for the extreme points of a polytope, we can often say that it holds for all the behaviors contained in the convex hull of these points. So it turns out that if you have something in this higher dimensional 16-dimensional space that's a nice polygon like this, then you can express it as the convex hull of its vertices. And so this no signaling set has these extreme points, and then any valid probability distribution contained in this outer square can be expressed as a convex combination of these extreme points that we see at the points. So in particular, if you have a quantum probability distribution that might be like here, for instance, maybe that quantum probability distribution can be expressed as a weight of a little bit on this point of the no signaling set, plus a little bit of this point on the no signaling set, and maybe a little bit of this point on the no signaling set. So that quantum probability distribution is expressible as a convex combination of the extreme points of this no signaling set. And so then if we can say something's true about the extreme points of this no signaling set, then if that property has the convexity property, then we can say that that property also holds of this quantum point that's contained in the convex hull of these extreme points. So that's why we're trying to contain the quantum set of probabilities, which is known to have this tricky curved boundary, in a larger polytope. We've got this no signaling set, and it's a polytope, it's a polygon, which means it has a finite number of vertices. The quantum set doesn't. The quantum set is just some crazy circular ellipsoid thing, but the no signaling set has a finite number of vertices. If we can say something is true of the vertices of the no signaling set, we can say that it's true of everything contained in there. Not every property, but a lot of properties turn out to be of the form that if you can say it's true for X and Y, then it's also true for any mixture of X and Y. That happens to be true for a lot of important things. It's convexity property. So that's why we're trying to do this. And so we've contained the quantum set within this no signaling set that was defined by these conditions that, you know, a certain collection of Bob's probabilities have to be independent of Alice's setting choice. And here are some of the extreme points of the no signaling polytope. These are behaviors that are no signaling. They obey those conditions. And there's the polytope, the polygon of these no signaling behaviors has 24 extreme points. These are 2 examples of it. And so if you take those 24 extreme points, then by mixing various weights of those 24 extreme points, you can obtain any quantum achievable distribution. Now, the approximation we get from the no signaling set contains a lot of junk that's non-quantum. It's all the way out here. And so what we want to do is we want to get a better approximation. We want to get a better polygon approximation. And so that's kind of what we've been doing in this most recent paper that I wrote with Yanbao Zhang in you know, just about to be published in New Journal of Physics, is we were studying ways to improve these approximations of the quantum set. And what we did is, you know, we had these no signaling conditions, and now what we're going to do is we're going to include another hyperplane determined by the Tsirelson bound. And so here's the Tsirelson bound, which is, it bounds the maximal possible violation of the CHSH inequality. This was discovered by Tsirelson around 1980. And the Tsirelson inequality is just a linear combination of these probabilities. And it says that that linear combination of these probabilities has to be less than or equal to 2 square root 2. And now, remember, we're in this big space R16. And what does a constraint like this look like? Turns out that it's a hyperplane. It defines a half space. It cuts R16 right in half. And then half the points in R16 are less than this amount, and half of them are more than this amount. And that's going to chop off a corner of our no signaling polytope. So what this Tsirelson bound is we incorporate it. And when we're looking at a 2-dimensional slice, the Tsirelson bound says, okay, you know, only points on this side of this dotted line are quantum achievable. So, so we incorporate that Tsirelson bound that chops off a half space. And in our work, we've also studied these tilted Tsirelson inequalities. There are more of these Tsirelson type inequalities that result in other half spaces we can incorporate. And so this schematic drawing for better approximations of the quantum set says, okay, now I've got these, you know, the Tsirelson, if I project down and I look at just a 2-dimensional slice of this 16-dimensional space, I get something that looks kind of like this, where I've got the quantum set, and then the Tsirelson inequality chops off half the space and says quantum things are only on this side of this dotted line. And then this is denoted by a 6. This is a tilted Tsirelson inequality. And we can say, okay, the quantum set's only on this side of this line. And so now all of a sudden, instead of containing the quantum set in this big no signaling square, we're starting to contain it in kind of like an octagon, something like that. We're getting a better approximation. And the extreme points of this octagon, schematically, we can think of them as occurring where, you know, these 2 dotted lines occur right here. They intersect right here. That might be an extreme point. You know, this dashed line intersects this thing right here. then you know, that might be another extreme point in this higher dimensional thing. And so we classified that in our recent paper. You know, the abstract of my talk contains the information for what paper that is. And the extreme points can be found algorithmically by a linear program given any constraints. But what we were able to do is get some analytical results yielding a formula for the extreme points as a family of polytopes parameterized by alpha. Alpha parameterizes the degree of tilt in this sort of tilted Bell inequality here. So, you know, there's many different 6 lines. They could be, you know, angled at very different things. Alpha parameterizes that tilt. And we found the extreme points of the polytope given in terms of these convex weightings of the extreme points of the original no signaling polytope. So, that's kind of our main result, but it's mostly interesting for how it helped us improve randomness generation. So I've only got about 4 minutes left, including my question time. So I'm going to try to kind of just give a very high level overview of that. We have quantum distributions that violate Bell inequalities have to contain some randomness. I'm talking about it a little bit on this slide. And I talk about this at length at my last Quilt Day talk. So, you know, here's the YouTube link for my last Quilt Day talk. I don't have time to talk about that intuition today. But if you're violating, it turns out if you're violating a Bell inequality and you've got an Alice over here and a Bob over here, you've got some randomness that just cannot be predicted, even if, you know, unless you're violating signaling faster than the speed of light. And so having this certifiable randomness can be very useful in a thing. And what was important about getting this polytope approximation to the quantum set was that we were able to find these functions that sort of witness the amount of certifiable randomness. It helps us better find these functions that witness the amount of certifiable randomness. And I'm not going to go into my next slides because I do want to leave some time for some questions. But the basic idea is we have a, when we're trying to determine whether or not a particular function witnesses the presence of randomness, we can prove that it is valid for all quantum distributions by proving only that it's valid for these distributions that contain the quantum set in their convex hull. So we found that, you know, we want to sort of come up with the best function that sort of estimates from experimental data how much certifiable randomness is in the data of a Bell experiment. And the first thing we did is we said, okay, let's check whether these functions are valid or not by checking whether or not they're valid for the extreme points of the no signaling polytope. And then our next idea was like, well, let's incorporate the Tsirelson bound, and then let's optimize these functions under the constraint that they have to be valid for the extreme points of this Tsirelson polytope, where we check at all these values. And then we get an even better approximation by incorporating these other Tsirelson bounds. And so then all of a sudden we are optimizing the set of functions that are valid for the extreme points corresponding to all these sort of like hexagon points around the quantum set. And it turns out by getting a better and better approximation of the quantum set, we get better and better functions that we can find for certifying the amount of randomness. I'll give you my little money slide. By doing this better approximation, the expected number of random bits that we can certify an experiment, we were able to increase it by about 18%. And we were able to optimize the amount of tilt in this sort of thing and get sort of a numerical optimization. Yeah, it was good. We're getting more randomness. And current research, we're applying these techniques for other things, like calculating the quantum intrinsic non-locality of quantum distributions, and really trying to find the root resources for device-independent quantum tasks. I'm going to be advertising for a postdoc position. So if you're interested in this or multi-party non-locality, keep an eye open for that this fall. Starting next fall is when the position will start. We'll be advertising for it this fall. So I've used all of my 30 minutes, so I'll